Well, welcome everyone to the Air-Sea Fluxus from Space webinar series. Today we have Igor Uchoa, who's going to talk about some of the work he's doing. And I'll let you take it away, Igor.
Thank you. Let's see if I can make this work. Is everybody seeing?
Looks good.
Okay. All right. First of all, thank you everyone for the Oasis group for inviting me to this talk. My name is Igor, and today I'm going to present some of my work on my second chapter of my thesis entitled Observe Rapid Adjustment of Atmospheric Boundary Layer to Submesoscale Sea Surface Temperature Fronts. Like I said, this is the second chapter of my thesis in collaboration with my advisor, Jacob Winograd, and folks over at Hui, Oregon State, and Scripps. So let's just try to right in. As we know, this is the right group to talk about this. Like air-sea interaction is important, and it's mostly divided in two different regimes. We have the more studied and more known, where large scale ocean variability is driven by atmosphere large scale. So that's where we get our ocean driven gyres. But somehow maybe more interesting is the mesoscale variability acting on the lower portion of atmosphere, changing the variability of the atmospheric boundary layer, either by spatial SST variability or current variability through the thermal and current feedback and other mechanisms for air-sea coupling. And here I'm showing an SST image from Muir showing this upwelling front in the California coast, where we see these meanders and an SST variability. And this is imprinting in the atmosphere that can change the variability, which we know that it's important. But we also know that the ocean has more variability than just the mesoscale. The submesoscale variability, these filaments and fronts from or varying from 10 kilometers to 100 meters, show a different dynamical regime of mesoscale, and then can be important for our interaction. But they're challenging to observe and model. So submesoscale dynamical regime has fast evolving instabilities in the orders of inertia period and spatial scales close to the planetary boundary layer and the atmosphere, and very sharp gradients, especially in sea surface temperature. And this violates the previous assumptions we make for SC interaction at the mesoscale. And here on the panel on the right, this is a diagram and from this white paper on this workshop in air-sea interactions on 2024, where we can see this new concept that we came up with of air-sea interaction at the submesoscale. So the submesoscale air-sea interaction scale, and it's encompassing of atmospheric mesoscale and submesoscale and small mesoscale in the ocean. And it's really connecting these two spatial scales from both fluids that have similar spatial variability and temporal variability, but also are within the uncertainty range of forward and inverse cascade, which can play a important role in the dynamics and may add degree of complexity when we're understanding air-sea interaction. So like I said, submesoscale features have spatial scales that are close to planetary boundary layer, and sharp gradients that can mean strong heat fluxes and momentum fluxes, but we do not have necessarily a good observational background to back that up. And even with models, it's really hard to model in high resolution in LES because they're computationally costly. So this is a challenge when it comes to air-sea interaction at submesoscale. And just to summarize the motivation, we have that submesoscale dynamics violates this framework for mesoscale due to the characteristics that I just talked about. Um, and this can impact how we understand air-sea fluxes for climate and weather models. So we need this observational background to um, give us ground truth of what is happening so we can model these fluxes better and decoupling. And observing submesoscale air-sea interaction becomes relevant for, again, global and climate models, but also for ocean atmosphere satellite missions. Um, so thinking of that, we can move on to how these air-sea fluxes are happening, the mechanisms that are contributing to air-sea interaction at the submesoscale. We're going to focus today on the thermofeedback, which is this all-encompassing term for changes um, in the atmospheric boundary layer by SST variability. This term sometimes defines a lot of the mechanisms. There are also dependent on scales. There are purely changing the atmosphere by SST variability. We have the pressure adjustment on larger scales by Linzen in the GUM. But today we're going to focus on this mechanism that is the concept that is most accepted for submesoscale on changing wind speeds at the surface, which is the turbulence-driven response or downward momentum mixing that involves stress divergence modulations and turbulent boundary layer modulations. There's also another mechanism that changes the attipotential energy flux response in the surface ocean. This is explored in my first paper of thesis, but I will not talk about this in this talk. We can talk about it a little bit in the Q&A, but today I'm going to focus on the turbulence-driven response. So how does that mechanism happen? We can think of this idealized submesoscale SST front, where we have this cold SST section and a warm SST section. We have wind blowing from cold to warm, and the modulation of this turbulent boundary layer. So over the cold, there's cooling, there's a formation of this internal boundary layer, and suppression of mixing and vertical velocities, which why we see this shearing wind. And in the surface, this relatively smaller wind at the surface. When it comes to the warm part of the submesoscale front, convective instability is enhanced. So momentum is being brought from aloft to the surface. There's this homogenization of the air column, and what the end product is the accelerated winds at the surface. So this complex turbulent momentum mixing mechanism, it can be easily translated to this correlation between SST anomalies and wind speed, this positive correlation. Even though the mechanism itself, it's not as simple and also asymmetric. So when the wind is blowing from warm to cold, momentum cannot be unmixed. So the conceptual way of thinking of that is the physical interpretation of thinking is that because the internal boundary layer is smaller over the cold part of the submesoscale front, the the integrated wind stress is higher at that column, and then that's why we see decelerated winds over the comparing to the one part of the front. And as you can probably guess, this is really hard to observe at the submesoscale. Again, very fast evolving instabilities, small scale spatial variability, and we would have to observe this multiple times to give a composite, more statistical analysis if this is actually what is happening at the submesoscale. And that's where the S-mode mission comes into play. I was part of this one of the missions from the S-mode, the submesoscale ocean dynamics experiment, where one of their goals was to quantify the role of air sea interaction and surface forcing and submesoscale variability. This was off the coast of San Francisco and was a multi-instrument and multi-platform mission. As you can see here, there's a myriad of instruments that are measuring submesoscale fronts from shipborne, airborne, and automotive profilers. Today, we're going to focus on the shipboard instruments and the airborne instruments from the B200 that I'm going to go slightly more into detail. So the airborne instruments measured 10 meters winds from the Doppler scat, which is this Doppler scatterometer, and that measures winds and currents at 200-meter resolution, enough to observe submesoscale variability. And we are also using MOSES, which is this instrument that measures sea surface temperature and a striking resolution of approximately 5 meters. That also, of course, encompasses the submesoscale variability. And we can see that we can use those airborne instruments to look at snapshots of wind and SST, see if there's, at small scales, at submesoscale, if there is any correlation between the two, like we observe in mesoscale. And we can use the shipborne instruments to have a vertical view of the mechanism and see what's happening there. The shipborne instruments contain the usual equal CTD measuring temperature at every 5 minutes approximately, and the meteorological station measuring surface variables like sea surface temperature, surface winds and heat fluxes, heat flux components. But what is novel here is the use of this upward LiDAR, the wind cube, that measures winds from 50 meters to 200 meters at a frequency rate of 4 seconds. And the use of radiosonde transects on some of the sections that we measured, giving us information of the air column for temperature, wind profiles, relative humidity, and etc. So with the combination of those two platforms, we can have sections of the submesoscale fronts and also observing what's happening in the atmosphere for each transect in a high frequency rate. So that's exactly what we did. So here we are showing one image of SST using Sentinel-3. We can see the filaments and some mesoscale fronts embedded into this large mesoscale front. The black transects on panel A show all of the transects done by the IOP1 of S mode. In total, we have 63 transects. And if we zoom in this using MOSES and Doppler scat, we can observe the variability of SST and wind stress on panel B and C. And we can already observe this first. At first, there is this spatial correlation between sea surface temperature variability and wind stress anomaly, which gives us the first indication that at submesoscale, this phenomenon is active, just like at the mesoscale. Um, and so we can move on to the shipborne measurements to look at the vertical structure in the ocean and the atmosphere. Just as a background, we can look at the background conditions of the region for the month of the survey. So it occurred on October 2022, and this is using for the panel. For the left panels here, we see ERA5 reanalysis monthly average for October 2022. Sea surface temperature shows this upwelling front with the instabilities, mesoscale instabilities, and associated with this SST gradient. And this is also imprinted in the air temperature at 2 meters with a slightly more animal temperatures. We can see a predominantly northwest wind blowing over the region and a marine boundary layer that is with gradients that are similar to the SST variability in the region. We can also look at the time series of marine boundary layer, wind speed, and wind direction. Here on the right, we have in purple the reanalysis outputs for the region. In the green dots, we have the radiosonde measurements for marine boundary layer, wind speed, and wind direction. And in red, we have wind cube, the upward LiDAR measurements for 50 meters. And you can see that they agree pretty well in an average sense, which give us confidence that ERA5 is also doing a good job at showing these modulations. We can observe that the wind was mostly from north-northwest, but there is between 16 and 19 of October, there was this cold front passing, which did not affect the background average analysis that we were making for the transects. But it's important to mention. So with all of that in mind, what we did for our analysis was to use all of our transects and interpolate that into a cross-front along tract frame where we can separate the negative velocities for our interpolated sections to the cold SST and our positive distance for warm SST. And we can average all of these transects together to give us a composite of the spatial anomalies for each of the variables that we're interested, especially SST, heat fluxes, wind speed, and vertical wind shear. So first we can look at the composite for the ocean front. We have here strong SST variability from cold to warm and associated heat fluxes in the order of 40 watts per meter squared, which are strong heat fluxes that they're potentially driving changes in the atmospheric boundary layer. We can look at vertical wind shear anomaly. So this gives us an idea of how homogenized the wind profile is. So for the warm part, we see negative anomalies for vertical wind shear, representing this homogenization of a wind profile. And over the cold, we see a stronger vertical wind shear anomaly, positive vertical wind shear anomaly, which indicates a more sheared wind profile. And that's consistent with the mechanism that we're trying to explain, where convective instability over the warm give us a more homogenized wind profile. So again, negative and positive, negative correlation between SST and vertical wind shear. And for wind speed, we can see at the surface, there's this positive correlation between SST and wind speed. So over the warm part, accelerated winds, and over the cold, decelerated winds, which again is corresponding with the mechanism that for downward momentum mixing. But we observe this negative wind speed anomaly aloft over the warm SST, which is due to this mixing of momentum from aloft to the surface. So if there's an acceleration of the wind on the surface, there's also a deceleration of the winds aloft, and then that's why we're observing this negative inversion here, which is also consistent with the change in vertical wind shear profiles. Okay, so we have this picture here that indicates that downward momentum mixing, that this mechanism of thermofeedback is occurring at in submesoscales and submesoscale features is robust because this is over a month that we're using 63 transects measuring these fronts and filaments. But we can give a more statistical analysis to this mechanism as is applied in mesoscale. So the first step is to compute coupling coefficients on using wind speed and SST. The colors here, this is a SST bind scatter plot. And the colors in gray here represent all of the grid points that we compute our correlation with that are from the composite interpolated sections. And the colored points here are the SST bind scatter plot. We see this coupling coefficient, this slope, this regression slope of 0.23, that is similar to mesoscale coupling coefficients. And but the difference here, or the key point here, is that some mesoscale have higher SST gradients. So that means potentially there is more forcing of wind speed generated by this SST at the submesoscale. We can look at also vertical wind shear correlations. We see this negative correlation as was shown by the composites, and this can give us how efficient SST variability is homogenizing the air column, for example. And this hasn't been appropriately necessarily measured at the mesoscale. So this is maybe a new way to look at this thermofeedback. And then we can also look at lag correlations and also vertical structure of how these correlations are changing vertically. So mesoscale, as I mentioned in the beginning of the talk, have characteristics that violate the assumptions that we make for SST interaction at the mesoscale. One of them is that they're fast evolving. They have spatial availability that is are higher than mesoscale, and this gives us one of these characteristics is that submesoscale is most likely influenced by advection. So we wanted to check that, and then the way that we do that is by looking at correlations, lag correlations, and this is showing here on panel C. We're seeing correlation of wind speed and SST anomalies, and then how they change as we increase or decrease lag, and also if we look at different layers of the atmosphere. So this may be too much information, but I'm going to go through parts here. At zero lag, as a normal correlation, we have a positive Pearson's R showing a positive correlation between SST and wind speed. But as we increase lag, meaning how changes in wind speed are associated with SST modulations that are downstream of the front, we can see that there's enhancement of correlation, which is likely due to advection. So this gives us the indication that advection is playing a role, changing this the signal driven by downward momentum mixing downstream of the front. We can also look at the vertical structure, and we see this inversion of correlations. That is exactly what we saw in the interpolated composite section, where there's this redistribution of momentum mixing that's bringing high momentum, like higher momentum to near surface, and that's going to represent a negative anomaly at aloft above this internal boundary layer. And that's what we're seeing here. If we look at vertical wind shear and SST correlations, again, we see an enhanced correlation as we increase legs, and the higher vertical wind shear correlations are associated with this inversion in SST and wind speed correlation. So now that we have this statistical analysis description, this gives us the indication that advection is also playing a role together with the downward momentum mixing, but we wanted to give more of a dynamical interpretation to if that's actually true, and then how can we confirm that. We have many variables we have variables that can contribute to the downward momentum mixing and the advection, and we can explore them to give a scale analysis using those variables to observe if advection is actually playing a role and downward momentum mixing, where are the time scale adjustments of both of these mechanisms. So here we have, coming back to our composites, we're showing wind speed sections and the SST. We have a lot of information about the length scale of the front. We have background wind. We have the changes in wind speed between cold and warm. We have the depth of the internal boundary layer, and based on wind stress, we have the friction velocity. So we can use all of that information to give us a scale analysis of time adjustment of downward momentum mixing and advection. So doing the time scale adjustment analysis, we observed that these have similar time scales, which again gives us the indication that advection is playing a role in this mechanism. So again, the time adjustments are order the ratio of them are order 1, which gives an equal contribution for this. We also looked at the pressure adjustment just as a sanity check, see if these are valid. We expect them to not be playing a role for submesoscale. I'm showing here a composite of the pressure anomaly for all the fronts, just like I did for the interpolated sections. I'm using surface pressure. As you can see, it's difficult to disentangle the trend here from cold to warm, which already gives us the idea that this is not playing a role at such small scales. But if we use a change in 1 Pascal between cold and warm to 10 pascals and then look at the time adjustment, we see that this time adjustment is 10 times higher than the time adjustments for advection and downward momentum mixing, which confirms that this is probably not playing a role at the submesoscale. And finally, the final part of the analysis is to look at case studies to see how, instead of looking at spatial anomalies, looking at how these variables are changing along the section. We chose those 2 sections here on October 24th due to favorable meteorological conditions. So the wind's going perfectly in line with the front here. And then for section 2, we observed that the northwest wind and the track are both aligned with this cross front SST, which we can use that information to calculate divergence for the wind, as I will show you in a few slides. For section one, not only the favorable meteorological conditions are good, and we have sufficient cross-front survey length, we also have radius on information for that front, so we can see air sea temperature and bulk Richardson number modulations over the front. So let's move on to the sections. So section one, again, shows the modulation of SST, the change in SST from cold to warm, and is also accompanied to that is the heat flux anomalies. We see a section of wind speed with decreased wind speeds in the surface for the cold part, and then increased wind speeds over the warm. We see this adjustment of the internal boundary layer that can be represented either by the magnitudes of the wind, but also the air temperature that is plotted in the black contours here. We see a more stratified column over the cold and a more mixed column of air temperature over the warm. For wind stress calculated by Doppler scat, we can also observe the correlation between cold and warm, the positive correlation, which also is consistent with the modulation of the internal boundary layer. We can look at not only vertical wind shear, but also changes in bulk Richardson number. So we can see the slope here of bulk Richardson number going upwards as we go to the warm part of the front, representing more convective instability, negative values, convective instability over the warm part. And then here again, we're showing vertical wind shear, total vertical wind shear, not the anomaly. So we can see reduced vertical wind shear over the warm, representing this more homogenized wind profile. And then for section two, we have this large survey of this warm filament here, showing the strong SST variability and air sea imbalance, the heat fluxes that are, again, order of 40 watts per meter squared, the adjustment of the internal boundary layer. So because we have a long section here, we can see that this high shear band is increasing over the warm, and then below that, the decreased vertical wind shear associated with this homogeneous wind profile. And I think the coolest part of this section is the calculation of the divergence, because again, due to the angle of the wind and the transect, we were able to approximate the total wind divergence in the transect, and then we're comparing that with Doppler scat divergence, and they match reasonably well, which is very exciting. And then, of course, this wind divergence pattern is indicative of vertical circulations in the edge of the front, which has been previously shown by LES models in the same way. Okay, so some take-home messages, and we can move on to questions. Submesoscale resolving measurements show that there is this fast adjustment of the lower atmosphere, driven by SST variability, even at small scales like submesoscale. The mechanism that is occurring is turbulent mixing, most likely, but there's also an important component of advection, modifying the momentum in the atmosphere and changing the structure of the planetary boundary layer. We can also observe the winds divergence over the lower 200 meters. There are coherent with vertical circulations on the order of 1 centimeter per second. They're similar to LES outputs. And finally, these observations are important for us to understand how air sea fluxes occur at submesoscale, and they're provide ground truth for weather and global numerical simulations. And with that, I'm happy to take any questions.
Well, thank you. Questions for Igor? Uh, Maybe while people are thinking of questions, I'll ask um, about what do you think the net impact of the submesoscale heat fluxes is on the global heat flux?
Um, I think that firstly, the sum net is not zero, right? They're impacting. There's likely an effect in across scale flux that we
Mhm.
cannot see here yet, but this should be accounted in global models, numerical models, because this actively changing how surface winds are surface winds variability. And yeah, I think that's on from the back of my head. That's like first thing that is I think is important is how changing the lower atmospheric boundary layer for sure.
Thanks. I see that Yolande has her hand up.
Yeah, thanks, Sarah. Nice talk. Thank you. Yeah, I just wondered, you did show a little bit of the ERA5 reanalysis in the beginning, and comparison seemed reasonable, but did you do a deeper dive with that? I'm just curious, kind of along the lines of Sarah's question, like the impacts of these processes on the current version of things like reanalysis models and how well they're capturing some of this. And also a side question would be, did they assimilate these data? Um, so yeah.
Um, so AirFi is definitely not assimilating submesoscale data into that. I we're comparing with the analysis that I did with Aero 5 was again just comparing the background conditions to see if they're acting the same because I did some comparisons with boundary layer measurements between radiosones and Aero 5, and I wanted to check if they're making sense. I have not checked into a more deeper dive into the cross-scale impacts. I think there's a lot of work to be done there. But there's some papers like Lusecki and collaborators have shown that the unresolved fluxes from small scale variability in heat fluxes are acting in the average larger scale total fluxes. Yeah, and then we make some discussion that on the paper, but I have not looked at into really into detail of those in those cross-scale fluxes yet. Um, I'm not sure if that answered your question.
It did. Yeah. Thank you.
Thanks.
Thanks. Looks like Megan Cronin is next.
Yeah, hi, thanks. Wondering, did you see any effects of the front on barometric pressure and whether that had impacts on the winds?
On pressure,
Yes.
we did look at that. We look at pressure to see if there was any pressure adjustment over the
Yes.
front, which was not expected because the scales are so small. And turns out like we don't see any like robust trend between those fronts. Again, small scales. It's and then time fast evolving, which would not allow for the pressure adjustment to occur effectively. Um, but yeah, this I guess the composites
Mhm.
show this trend. That's not really a trend. I wouldn't say that.
Uh-huh. Okay, that's interesting. Okay, thanks.
Thank you.
Jidong is next.
Thanks. I think one of the instrument from ESMO very unique is the shipborne upward-looking wind lidar, because that's the only instrument in my mind that can possibly observe atmospheric boundary layer role. I don't know whether during the field campaign, the wind shear is strong enough to generate such boundary layer rolls, and whether there are such signals in the wind profiler data.
I'm sorry, can you repeat the question again? So you're saying that you don't think that the atmospheric adjustment would be observed by the wind profiles?
No, in the atmosphere boundary layer, when the wind shear is strong enough, it will generate they call the rolls or large eddy, if you will, in the boundary layer. And the reason I'm asking this is, I think in your case as well, in most of the case, the airspace fluxes is treated as a 1D problem of micro scale turbulence, right? But once you have the rolls horizontal scales can be 1 to 10 kilometers that match the submesoscale structure of the ocean. If that's the case, the air-sea flux problem is no more a 1D problem. So the atmospheric rolls will play an explicit roles, two roles. One is double L, one is single L.
Yeah.
So before we answer that question, from ASMO, I just wonder whether number one, the wind shear is strong enough to generate a roll. Number two, whether in your wind profiler data, you can observe such kind of a roll.
Yeah, that's a good question. I think even with Doppler scat, I think there was you can see the mechanisms that would generate these kind of rolls. I'm not sure if that's thoroughly explored yet to see if there was the kind of rolls that you're talking about, but there were some signals. You're right that like the mechanism is not a 1D anymore when it comes to like the smaller scale like this. Even in the computation of the assumptions that we make for computing heat and momentum fluxes, right, from core, because due to the variability um, in these in this such small scale. Um, yeah, I'm not sure. I guess Lucas want to say something, or is
I
that?
was just going to chime in on this. It's a good point. We know there were atmospheric rolls during the SMO experiment because we picked it up with Doppler scat. Um, the trick here is if you want to sample atmospheric rolls, you have to go in the crosswind direction, which typically because the orientation of the front, we were in the upwind downwind direction, which was good for Igor's work. Um, the short answer is that there might have been some contamination for rolls, but because of the orientation of the flight leg, and because of the short duration it took to do those transect across the submesoscale front, I don't think this really impact Igor's story. To really look at those rolls, I mean, you're right. Looking at using a wind Doppler profiler like we had is the right tool. I just don't know if the ship is fast enough. And that's why atmospheric rolls have been typically studied from suborbital or orbital platform.
Great, thanks.
Yeah, thanks, Luke. Also, like the transect, the background picture that we show from the transects is pretty throughout with varying types of shears and wind magnitudes, and we can still see that signal. So I think it's somehow that's a pretty robust signal of the thermofeedback.
Thanks. Other questions? Maybe I'll come back to my original question. And you suggested that submesoscale processes should be parameterized. Do you think that we have enough information to know what that parameterization might look like?
I don't think we do yet, but we do have we like from this work, for example, we know that the coupling coefficient or the descorrelation is just as strong as mesoscale, right? And then
Mhm.
submesoscale is so it, as it doesn't give us the ideas on how to parameterize submesoscale, but it does say that these fluxes are important to be accounted. So resolution wise, it should be embedded in there. Yeah, and then yeah, I that's the short answer, I guess.
That seems like a challenging problem. I think the other question to ask is about resolution that we need. And that's especially a question if we think about future satellite systems that we can envision SAR-based systems that have pretty high resolution, things like what Harmony will provide, but small sampling patches, or we can imagine swath width systems, something like what Simmer will have for SST, with something more like 15-kilometer resolution, which is not quite the submesoscale. And so there's a question then how to put all the pieces together to from orbital strategies to get at some of the things that we might want
Yeah,
to know.
yeah. I think the most essential parts have similar scales that even if submesoscale resolving, not submesoscale
Mhm.
permitting, would be simultaneous with both of the instruments, right?
Mhm.
Of course, we didn't need 5 meter resolution for most, like to observe a submesoscale, but the fact they were in the same plane and then showed the same pattern was really important.
That's a useful point. Kaike has his hand up.
Hi, Igor. Great talk. I was wondering, I don't remember what range of wind speeds you were exploring, but I was wondering if, like, for lower wind speeds, you would expect that, like, you can resolve sharper submesoscale RC interactions, or maybe that, like, for lower wind speeds, you get, like, a time scale similar to the pressure anomaly time scale, and then those processes will become more important.
I don't I don't think the pressure adjustment would become important as we decrease wind, but the for that small submesoscale frame that we were looking at, but it would definitely decrease the impact on advection, so that like the most purely momentum mixing would come more into play. If we look at the time scales here, um, yeah, so the advection would be the effect of advection for that time adjustment would be decreased, but not for turbulent momentum mixing.
I see. Thanks.
Yeah, thank you.
Any other questions today? If not, let's thank Igor again for a really great talk and great discussion. Thanks everyone for participating.
Thank you.